Hi, I'm Claus Smitt, and I'm with the Agricultural Robotics and Engineering Department of the University of Bonn, and today I want to talk about our work explicitly incorporating spatial information to recurrent networks for agriculture. Agricultural robots are becoming a key component of the world food production, and their monitoring systems are at the center of them performing their tasks properly. And in this particular example, this weeding robot needs to tell the difference between weed and crop so that it can apply treatments to weeds only without damaging the crop in the process. In this other example, we can see a glasshouse monitoring robot that drives autonomously through the rows, and it takes videos from the crop as it drives through. In this case, we would be interested in detecting the peppers so we can count them, figure out if they are ripe, ready to be harvested, and as well to measure the volume of them to see what kind of quality we can expect from it. In both cases, their monitoring systems are key so that these tasks can be performed properly. The way you would usually do this is you will take images out of the sensors of your agricultural robot and you will pass it through some processing and obtain a detection like the ones that we saw in the video before. However, agricultural robots nowadays have rich spatial temporal information like videos of color images and depth images as well, giving you also an idea of the 3D structure of the scene that you're navigating through. You can also have the trajectory estimation of it so you know how the road moved throughout time. So the question is, can we incorporate all of this into a neural network, and would this improve monitoring overall? So if you were to run a frame through your neural network and you were to show the activations of it on top of that frame, this is how it would look like. And you can see that the activations are well aligned with what you want to detect, in this case, a pepper. So if now your robot moves a little bit and you take those activations and you show them in the upcoming frame, you will see that there's a slight shift because of the movement of the robot, but still those activations are very well aligned with the pepper that you want to detect. So this way you could use temporal information by just fusing all of these activations together and you would get a better monitoring system. However, if your robot moves a little bit too much and faster than expected, or you have an unreliable sensor that's dropping frames, which is a typical case in practice, there's going to be a big shift between your activations of the previous frame and the current frame. And if you were to combine all of these activations, your predictions will be completely off because of the shift between the activation and the pepper that you want to detect. So we need to do some extra processing to this in order to be able to use this information to improve our monitoring system. The way we want to tackle it is by using all the spatial temporal information that we said that's available in agricultural robots. And the way we will do it is, because we know how the robot moved from one frame to the other, and we have the depth images that gives us 3D information of the scene, we can reproject each channel of the tensors of the activations of our network into the next frame, and thus we can do spatial temporal registration. And the way we would incorporate this into a segmentation pipeline is started with your typical unit style architecture, and now we have the spatial priors that are the depth images from the previous frame and the trajectory of the robot. And we also have a temporal prior, which are the activations of the previous frame of the network. So now we can package our spatial temporal registration in a new layer that we're going to replace at the beginning of each depth of our encoder. And this layer would take both the spatial prior and the temporal prior. In order to tie our recursion, we're going to take the output of those layers and send it to the next frame. Here, it's a comparison between our spatial temporal model and a baseline segmentation one, and we can see that it's able to produce sharper masks without having a spill into the leaves. And this is very important because if, for example, we want to measure the volume of a pepper, we want to have a precise mask that tells us only where the pepper is and not take the leaf as part of our measurement. In the case of arable farming, we are going to be able to see that our spatial temporal model is able to detect crops that the baseline system is not able to, and it also produces sharper masks. In this case, sharper masks mean a better estimation, for example, of the leaf area index, which is key to determine how good your crop is doing in an arable farming setting. So today I show you how you can incorporate explicitly spatial temporal information that's available in most agricultural robots to convolutional network monitoring systems. We also show that this improves the monitoring in challenging agricultural scenarios, and we also discussed that it's robust to sensor errors because it doesn't rely on your robot running at a specific speed, nor to have constant frame rates from your sensors. If you're interested in the details of our work, please go ahead and scan our QR code to get our paper, code, and data. Thank you very much.